Hello everyone. Today we would like to present to you our final project, open source ventilator with my teammates Zeynep and Kadircan. A ventilator is a machine that provides mechanical ventilation by moving breathable air into and out of the lungs to deliver breath to a patient who is physically unable to breathe or breathing insufficiently. And the ventilator is a way of measuring and controlling the volume pumped and the breath rate, monitoring for inspiratory pressure and inspiratory to expiratory time ratio. This project is developed for R&D purposes, not to be used directly on the patients in the hospital at the first stage. As you know, the virus has become uncontrollable and continues to cause various respiratory ailments all over the world. The number of ventilators is starting to become inadequate, so it's time for us to take the initiative. We aim to produce this respirator with 5 main goals, as you can see.
Our design consists of 5 main parts. First, we supply the air system with air compressor. Then we bring the pressure of the air entering the system to desired level with the flow control regulator. In this way, we constantly control the pressure of air entering the system and ensure the content of the system. Sprinkle valve is the most important part. Thanks to the solenoid in the sprinkle valve, it ensures that air goes to test lung or not. We adjust the inhalation and exhalation event by giving the current to sprinkle valve. We create an airway using PVC tube, and finally the test lung is connected to this tube. We create the electronic part using Arduino. In addition, we made our system user-friendly by using LCD screen LEDs and potentiometers. We constantly measure our pressure values by using a pressure sensor, and we provide the pressure control of the system for the second time. For example, in case of decrease or increase in pressure, our system gives a warning. You can also see other electronic devices we use. This is our prototype. Our system has 2 main functions. These functions are breathing time and IE ratio. Both of these functions can be adjusted using potentiometers, and currently used mode can be displayed on the LCD screen. Breathing time: a normal person breathes 12 to 20 times per minute, so breathing time circles are 3, 4, and 5. IE ratio: the IE ratio denotes the proportion of each breath circle devoted to inspiration and expiration phases. We have 1, 1, 1, 2, and 1, 3 IE ratio. So we can operate the device with 9 different functions. In this video, you can see the working stage of our system.
So for the mathematical modeling, main issue was deciding on the type of the model, since we aim to design the best convenient way for the doctors. So we choose volume controlled ventilation model, which delivers constant flow rate during inspiration until the set volume is entirely delivered, which provides the user to change the settings more comfortably. We have 3 assumptions. We assume that air follows the ideal gas laws, no air leakage in the system, and it follows the quasi-balanced dynamic process. Thus, all calculations are made accordingly. Critical in the model is the airway pressures, which are peak and plateau. Peak pressure is the pressure that is generated by the ventilator to overcome airway resistance, whereas the plateau pressure is the pressure that is essentially left over in the lung after the tidal volume has been delivered. Also, more importantly, there are compliance airway and airway resistance, which was the main goal in the model to calculate. Very basically, resistance describes the opposition to a gas flowing into the airways during inspiration, and the compliance describes the elastic property of the respiratory system. This same concept is crucial, since wrong calculation could end up severe diseases in the patient, such as bronchospasm, mucus plugging, and edema in the airways. And on the left, you can see our modeling results. And on the right side, we were able to plot a pressure time graph when A ratio is 1:1. We had the opportunity to compare our results with the pressure sensor that we utilize in our system. Since the tendency is succeeded, that was a sign of the success for our project. Also, you can see our answer analysis on the left. So here you can also see the final plots of our breathing ratio 1:2 and 1:3. One key point is that decrease in breathing ratio causes increase in flow rate. And finally, we choose to use the ratio 1:1, 1:2, and 1:3, where the expiratory phase is set longer than the inspiratory phase to more closely mimic normal cycle physiologic breathing.
We managed to make this project work with a limited budget in a short period of 2 months. Of course, there are aspects that are open to improvement in the project. For example, we used a household compressor for price performance. A medical compressor can be integrated into the system, and by adding more sensors, different data comparisons can be made. At the same time, we used PVC tube in terms of weight and budget. The tube can be produced using a higher quality material. Also, we designed our system using 3 different IE ratios and 3 different rating times in our Arduino code. We offered 9 different options in total, and the number of options can be increased by developing the code. Of course, we encountered some challenges in the project, and we encountered many problems, especially while installing the electrical system. Our Arduino was burnt, and some sensors became unusable when we used too much voltage. And despite all these challenges, we managed to complete this project in working order by using our engineering knowledge gained from our valuable professors. And since the first year of university, we have completed all the machine projects in the same group, 3 of us. I would also like to thank my teammates in front of you who have worked with the team in spite of all the difficulties. Thank you for listening.